Okay, so what we're going to look at with this chapter is some really cool things with derivatives and how they kind of work together. It's really makes some really neat things happen here. So we're going to start off talking about the mean value theorem for derivatives. And what is that? Well, the mean value theorem says that if you have some function and it's continuous at every point of a closed interval, and you can take the derivative at every point of its interior, not including endpoints, and that's differentiable, that means take the derivative, then there's at least one point in there, at least one point, xy coordinate, where the derivative at that point is equal to the slope at that point. Really cool, because that's what a derivative is. It is the slope of an equation at a specific point. So this just says that if we've got a closed interval and a continuous function, that we can do this really neat kind of thing here. So what we're going to do is we're going to take the function x squared, really simple, and we're going to show that it satisfies the mean value theorem, the MVT, from 0 to 2. Determine the value of c where the solution to the MVT, the mean value theorem for that equation would be. So here's what we're going to do. If you'll go back to basic algebra 1 skills, we're going to remember that f of b minus f of a over b minus a has the exact same shape as y2 minus y1 over x2 minus x1, the exact same shape. Okay, and so let's go and crank through our derivative. The derivative of x squared is 2x. In this case, a is 0, b is 2. We let 2x, that's our derivative, equal the slope at that point. So we just 2 squared minus 0 squared over 2 minus 0. And then we set 2x equal to the number we get over there. Well, in this case, then we're going to find out that x is 1. Hey, how about that? And that's how the mean value theorem works. Okay, you're going to take a derivative and you're going to just set it equal to the slope at that point. And we're guaranteed to get that if we have a continuous function on a closed interval where you can take a derivative at every single point. Okay, let's look at a couple instances now where the mean value theorem might not work so well. And remember, in order for this to happen, in order for the mean value theorem to work, you have to be continuous and differentiable on a specific closed interval, okay? And as long as we've got those two things, we are off and running. So what we are going to do is just kind of check these guys out and find out, hey, are they really continuous? Are they really differentiable over on a closed interval? So we'll just start with we'll start over here with x squared plus 1. And remember, if you graph this, the square root of x squared is just absolute value x plus 1. And notice what happens when you graph absolute value x. You get a corner point. And if you have a corner point, you don't have a derivative. Okay? Now, we could take this guy and we could go, all right, this works if we look at different different intervals. Okay, like from -2 to 0 or from 0 to 1. But if we go across 0 at all, like from -1 to 1, we can't do it. We can't find the mean value for that particular guy. Okay, and so we could go -3, 0, or whatever, but we can't look at anything that includes 0 in it because you can't take a derivative at a corner. The next one then says that if we've got x cubed plus 3 for all values of x less than 1 and x squared plus 1 for all values greater than or equal to 1, well, right away my calculus senses are tingling. I want to know what the heck is going on at 1, because if these two functions don't meet at that point, we don't have anything that will work for the mean value theorem. So I'm just going to plug 1 in for both of these guys, and lo and behold, I get two separate values. I get some sort of curvy thing for the x cubed part, and I'm going to get some sort of parabola thing for the x squared part. And look, they don't touch. They don't touch at all. And since it's not continuous, I can't take a derivative. And it fails both of those parts for the mean value theorem. So that's why these two guys, sometimes you just have to check and see, can you or can you not? And in this case, with both of these examples, because they are fail derivative on an interval, the mean value theorem won't work. Okay, look at this complicated piece of work right here. We're going to let f of x equal the square root of 1 minus x squared, and we're going to look at two different points, A and B. Okay, A is at -1, f of -1. b is at 1, f of 1. So remember, those are specific points. A function of 1 is the y value. Okay. Find the tangent to f in the interval from -1 to 1 that is parallel to the secant AB. What's going on? Well, here's what's going on. Let's graph this guy, and we're going to go from A to B on the x-axis. We're going to start at -1 on the x-axis and go to +1 on the x-axis. So that's what we're going to do. And working this guy out, we're going to graph him right here. Look, oh, half a circle. Look at that, half a circle. Why? Because if you just plug in those values, you get zeros, all right? And if you plug in a 0 for x, you get a 1. And if you plug in like a half or a fourth or whatever, it's going to end up making a semicircle, all right? And so this is what it looks like. Well, what we want to do is we've got this secant AB. And so what we want to do is find this horizontal tangent line up here, the red horizontal tangent line. So how are we going to do that? Well, we're going to take derivative, and when we take derivative, we're going to have to chain out this guy. So our big problem is a square root problem. That's the big problem. We're going to take the derivative of square root, so it's going to be 1/2 times the stuff, all right, and then 1/2 minus 1. So we're going to have 1/2 times 1 minus x squared to the -1/2 power. And then you take derivative inside that guy. So we're taking the derivative inside now of 1 minus x squared, and that's going to be -2x. And then put together all the pieces that can go together, because we want to work with as clean an equation as we possibly can. So the 2's actually divide out, and I'm going to rewrite this guy so that we've got a numerator-denominator situation. Why? Because I want to know if I'm going to find this extreme value in here, then I need to know what my max or min value is going, where it's going to be located. And it can only be located in a couple of places, either at an endpoint, 1 or -1, or where my derivative is equal to 0 in the numerator, or where my derivative is equal to 0 in the denominator, which means that the derivative does not exist. So I'm going to check both, I'm going to solve both of these guys out. I'm also going to look for that mean value theorem, because that's part of finding that tangent, all right? And since we're in the mean value theorem section, and so when I do all of this, it turns out that I get 0 for my mean value. So I start checking all these different things out. I plug in all my different numbers. I solve all the different things out, and I get 0, and I get 1 and -1 for my 3 big values, okay, to check. Well, 1 and -1 are my minimums, okay? There's no tangent line going on there. That's where I get that 0 in the denominator. But when x is equal to 0, I do have a max value that does make my mean value theorem work. I do get a coordinate there of the point 0, 1. And what does that mean? That means that the equation y equals 1 is the tangent line from the interval from -1 to 1 that's parallel to the secant. Wow, a lot going on there, and it's just a really cool problem.
The code is Assassin's Creed.
Assassin's Creed, there you go. Okay, so here's some things that we can pick up from looking at the first derivative of a function, and it's really kind of interesting. So here's what we're going to do. We're going to talk about where f increases, where your function increases, and it increases as long as you increase x value. So you go from like 1 to 2 to 3, or -1 towards 0, or something like that, where your x values are always increasing. And if your x values are always increasing, the matching y values always increase. That's an increasing function. F decreases if your x values are always increasing, so you're going from -1 towards 2 towards 10, but your y values now, instead of growing up, are now growing down, okay? And so if that happens, your function decreases. Well, here's a cool thing. If you look at your derivative, wherever the derivative is greater than 0, your original function increases, and wherever your derivative is less than 0, your original function is decreasing. That's really cool. Also, wherever your original function, or wherever the derivative is actually equal to 0, then you're looking at a constant at those places where it's equal to 0. So this is really some really neat stuff that's going on here. And then a last little tidbit is, if you have two derivatives and they equal each other, like if you have f prime of x and it's equal to g prime of x, then there's some constant that gives us our original function that we get the same function, but there's a constant difference. Like, for example, if I take x squared, okay, as a function, and x squared plus 3 as a function, the derivative of both of those is going to be 2x. Okay, so even though the derivative is the same, the original functions differ. So that's going to lead us towards a bigger pot of stuff here in just a little while. Okay, well, let's check out this example down here on the bottom. X cubed minus 4x. We want to know where this is increasing or decreasing. It's really easy. Find the derivative, 3x squared minus 4. Set it to be greater than 0 and set it to be less than 0. And where those things happen, that's where your original function increases or decreases. So on the left here, where we've got 3x squared minus 4 is greater than 0, when you solve that guy all the way down, taking all the steps necessary, and you square root both sides, then you're going to find when values of x are less than 2 over the square root of 3 units away from 0, you're going to have an increasing function, okay? Where if you work out the other side, you're going to have the same kind of situation where you've got x squared is less than 2 square roots of 2 over the square root of 3. So in between negative 2 square root of 3 and positive 2 square roots of 3, if you look on that right-hand side, that's where you're going to have a decreasing function. I think on the left I miswrote it. I've got x is greater than, and it needs to be greater than the whole way. So we could actually be greater than 2 square roots of 3, 2 over the square root of 3, or less than negative 2 over the square root of 3. I didn't put my negative sign on that very, very bottommost answer. And so that's where this function is increasing or decreasing. And if you figure out on your calculator the decimal value for 2 divided by square root of 3, and then you look at your calculator of the original graph of the function, those max and mins are the increases until you get to that max, and it decreases until you get to that min of the original function, and those values will match what we just discovered, okay? So, you know, here's where are you increasing? From negative infinity to negative 4 square roots of 3, and from negative 4 square roots of 3 to infinity, where are you decreasing? You're decreasing from negative 4 square roots of 3 to positive 4 square roots of 3. And you can leave it like this, or, I mean, we know what the square root of 4 is, it's 2. You could write it like that as well. So increasing, decreasing behavior, just use your, use what we know about greater than and less than, and let's just find those values where it makes a statement true. All right, now this is a really fun example to work with. We're going to kind of undo a derivative, as it were. So what we're going to do is we want to find a function who has a derivative of the sine of x, but whose graph passes through the point 0, 2. So they've given us the derivative sine x, and they've given us the point 0, 2. Those are two key critical things that we're going to need to know. And so what we're going to do is we're just going to ask ourselves, all right, if the derivative of what is equal to sine x? The derivative of what is equal to sine x? And if you think about it, you know, if you look at like any study aids that you have, or if you remember, the derivative of the cosine is the sine. So that's important, okay? The derivative of what is sine x, okay? So derivative of cosine is negative sine. Well, how can I get this to work out where when I take the derivative of the cosine, I get a positive sign? You make cosine negative. So what we end up with is negative cosine x plus c. So we're going back up, okay? We're anti-differentiating, and you see that right here defined underneath. So what happens next? Well, just double check yourself. Is the derivative of negative cosine x sine x? I think it is. So we're good to go. And then what we're going to do is we're going to use these values where x is equal to 0 and y is equal to 2, and we're going to plug them into our equation. And when we do that, we solve for c. So we're going to have f of x equals negative cosine x plus c, all right? And what we're going to do is we're going to substitute in 2 for y and 0 for x. So go ahead and fill in those things, and then solve this for c. So the cosine of 0 is 1, so I'm putting a negative in front of that. That's negative 1. and then y value is 2. So I have 2 equals -1 plus c. When I do that, I end up with c being equal to 3. So this then gives me my function, my original function of negative cosine x plus c, which is 3. Okay, that's how it works. Pretty cool, pretty cool. And don't forget plus c. That plus c part is key to the whole situation. All right. Now down here, the antiderivative, a function capital F of x is an antiderivative of a function little f of x if capital F prime is equal to f for every x in the domain of the function. The process of finding the antiderivative is called antidifferentiation. Another word for antidifferentiation is integration, and we will spend the whole second semester talking about that. But this is just a little glimmer into what we're discussing here. So if f of x is x cubed, then capital F prime of x would be 3x squared. Okay, notice the relation here. If I started down here with the f prime of x, when I find the antiderivative of it, I just go, okay, the derivative of what is 3x squared? And we have to think just a little bit, but it's not a hard thinking. Like, you know, if we've got x squared and it's a derivative, I had to have an x cubed. Now how do I get that 3 to go away and just become a 1? And you know, how does all that work? Well, it'll take a little bit of practice, but if you'll just notice some relationships right here, okay? I increase my exponent by 1. I go from 2 to 3, and then if you'll notice, I just divided by the 3 divided by 3, and that gives me 1. Okay, and so to really have the good antiderivative here, we need to make sure and add plus c. Why? Because I can put several different constants over there and get the exact same derivative every single time. So we need to recognize that there's a whole family of equations that go into this problem that when I take the derivative of them give me 3x squared. So that's how antidifferentiation works, and again, we're going to spend a lot of time talking about all kinds of different ways to use the antiderivative.